In 1929, at the Mount Wilson Observatory, an astronomer noticed something strange through the eyepiece of a telescope. Distant galaxies were all moving away from us. The farther the galaxy, the faster it was receding. The universe was expanding. Until that moment, most scientists believed the cosmos had always existed, in a quiet, unchanging state. But the data did not lie. Galaxies were scattering away from one another as if fleeing. This single observation overturned everything. Humanity thought it knew about the universe. Then, nearly 70 years later, another shock arrived. In 1998, two independent research teams measured the brightness of distant supernovae. The results defied all expectations. The universe was not just expanding, it was accelerating. Something invisible was pushing galaxies apart with increasing force. Scientists gave this unknown energy a name: dark energy. 3 physicists received the Nobel Prize for this discovery, and textbooks were rewritten. For 25 years after that, dark energy was treated as an unchanging constant. Then, in 2025, a telescope sitting in the middle of a desert sent back data that cracked that belief wide open. The composition of the universe is staggeringly lopsided. Everything visible, every star, planet, galaxy, and person accounts for just 5% of the total. 27% is dark matter, which neither emits nor reflects light, but reveals itself through gravity. The remaining 68% is dark energy. Dark energy works in the opposite direction to gravity. If gravity is the force that pulls matter together, dark energy is the force that pushes space itself apart. The tug of war between these two determines the fate of the universe. In 1917, Einstein added a single term to the equations of general relativity: the cosmological constant L. At the time, he believed the universe was static, and he needed this term to prevent gravitational collapse. But once the expansion of the universe was confirmed, he called it the biggest blunder of my life. Yet the 1998 discovery resurrected Einstein's so-called blunder. To explain the accelerating expansion, the cosmological constant was needed after all. For the next 25 years, the standard model of physics, known as LCDM, held firm: dark energy is a constant that does not change. That was the accepted answer printed in every textbook. But one project dared to question that answer: Arizona, the Kitt Peak National Observatory. At an elevation of 2,100 meters above the desert floor, the DESI telescope stands. DESI is short for the Dark Energy Spectroscopic Instrument. On the focal plane of this telescope, 5,000 robotic optical fibers are arranged in formation. Each fiber moves independently, targeting a different celestial object in the sky. At the same time, in a single exposure, it can capture light from 5,000 galaxies and quasars simultaneously. The goal of this project was singular: to build the largest and most precise three-dimensional map of the universe ever created. In March of 2025, DESI released its second batch of data: 15 million galaxies and quasars. This map contained the expansion history of the universe, stretching back 11 billion years. Scientists traced a pattern called Baryon acoustic oscillations within the data. These are the remnants of sound waves that rippled across the universe just after the Big Bang. The imprint acts as a cosmic ruler, marking a consistent distance between galaxies. By measuring how this ruler's spacing changed over time, researchers could track how the rate of expansion evolved. And what the data revealed was this: the influence of dark energy has been weakening compared to the past. For 25 years, the constant had never wavered. Now there was evidence that it might not be a constant at all. Before anything else, the reliability of this result must be examined. In science, the line between coincidence and discovery is drawn by the sigma value. The higher the sigma, the less likely the data is a product of chance. In particle physics, a new discovery requires 5 sigma to be officially recognized. In DESI's first data release, the sigma for dark energy variation was roughly 2.5. Intriguing, but far from conclusive. Then the second release arrived, with more than double the data, and the sigma climbed, somewhere between 2.8 and 4.2. This means the probability of the result, being a fluke, is less than 0.3%. It falls short of 5 sigma, but it is impossible to ignore. And it was precisely at this point that scientists encountered data pulling in an entirely different direction: supernova observations, cosmic microwave background measurements, gravitational lensing data. All 3 independent methods still aligned with LCDM, the model, in which dark energy is a constant Only DESI was telling a different story. When one measurement contradicts every other measurement, two possibilities exist. The first is that the measurement has uncovered new physics. The second is that a systematic error remains hidden somewhere in the analysis. In February of 2026, a research team raised the latter possibility. They suggested that a calibration offset of roughly 0.02 magnitudes in supernova brightness measurements could exist, and that this tiny discrepancy might be distorting the results. If dark energy truly is weakening, the destiny of the universe changes completely. Under the current standard model, the future is the big freeze. Galaxies drift apart without end. Stars exhaust their fuel and die, and the temperature approaches absolute zero. An eternity that is empty, cold, and dark. But if dark energy fades, gravity reclaims the upper hand. Expansion slows. It stops. And then reversal begins. Every galaxy collapsing back toward a single point, the Big Crunch. A rewind of the Big Bang that occurred 13.8 billion years ago. But the possibilities do not end there. A third scenario exists. What if dark energy is not simply weakening, but changing its very nature over time? Some theorists have proposed phantom energy. Phantom energy grows stronger as time passes. In this case, expansion accelerates beyond control, tearing apart not just galaxies, but stars, planets, and eventually atoms themselves. This scenario, called the Big Rip, is a finale in which every structure in the universe is annihilated. DESI's data does not yet confirm any of these three scenarios, but for the first time in 25 years, a meaningful crack has appeared in the default assumption that dark energy never changes. And another eye, already floating in space, is poised to investigate that crack. In July of 2023, the European Space Agency launched the Euclid Space Telescope. Its mission is to answer the same question DESI is pursuing. Is dark energy truly changing? Euclid observes the universe from the L2 Lagrange point, 1.5 million kilometers from Earth. Free from atmospheric interference, it captures billions of galaxies in infrared and visible light. Where DESI gathers spectroscopic data from the ground, Euclid gathers imaging data from space. If two completely different methods arrive at the same conclusion, only then can science claim confidence. Euclid's first major dataset is expected to be released in 2026, and DESI itself has not yet published even half of its total data. The final release is planned for 2028. If Euclid and DESI both point in the same direction simultaneously, LCDM will have to be revised. The standard model of physics will change. This is not simply a matter of adjusting a single number. It would alter the most fundamental understanding of where the universe came from and where it is headed. Just as Einstein introduced the cosmological constant, then abandoned it, then watched it return from the dead. The story of dark energy is far from over. At this very moment, DESI is scanning the sky above the Arizona desert. 5,000 optical fibers move without rest, recording the light of one galaxy after another. 1.5 million kilometers away, Euclid is quietly drawing the shape of the universe. The data these two eyes produce may answer the oldest question humanity has ever asked about the cosmos. Is the universe eternal, or does it have an end? In 1929, when an astronomer discovered that galaxies were moving away, no one fully grasped what it meant. In 1998, when the acceleration of expansion was confirmed, the same was true. And now we stand before data suggesting that acceleration may not last forever. The answer has not arrived yet, but the weight of the question has changed entirely. The universe may be rewriting its own fate. The next chapter of that story will likely open soon.